Welcome to this next lecture on sound and structural vibration. Last class we ended up saying we will study this paper, or we will derive some results from this paper, response of ribbed panels to reverberant acoustic fields by Maidanik. It's a 1962 JASA paper. So let's see, we need a Fourier transform pair definition. Okay, Fourier transform pair. So initially let's see 1D. For the 1D case, the forward transform, okay, I am doing the space version, so it's called the wave number transform also, but name doesn't matter. From space to wave number. So this is the spatial function. I take a transform and I will use I and j freely, okay, interchangeably as the square root of -1 dx. That's the forward transform. Then the inverse is 1 over twice pi integral minus infinity to infinity f of k e to the power plus j k x, this time dk. Okay, so we will just set up our convention through the delta function. So let us see. So this now, if I try to get back, okay, using circular arguments, so I have 1 over twice pi, I have integral minus infinity to infinity, then I have f of k, okay. So let me put e to the power of j k x dk here to begin with. F of k is integral, this one, okay, f of x1, the dummy variable, e to the power of minus j k x1 dx1, okay, that is equal to, so now left hand side is f of x, right, this is f of x. So if I take minus infinity to infinity here, then f of x1 dx1 here, okay, then integral minus, so this is minus infinity to infinity, 1 over twice pi e to the power minus j k x1 minus x dk. So note this here, that I have fx1 dx1 here, I have fx here, okay, and an integral over infinite domain So this has to be the delta function. Okay, so this has to be the delta function, this part, Dirac's delta function. Okay, which means what? Which means 1 by twice pi into minus integral minus infinity to infinity e to the power minus j k x1 minus x dk must be equal to delta x1 minus x. Okay, so if this is how you define delta, then the Fourier transform pair must be defined as it was. That's the idea. Okay, if we use this definition for delta function, then the way we define forward inverse transform conform to this definition. Let's look at 2D now, 2D Fourier transform. We have the forward f of kx comma ky is equal to the integral f of x comma y minus j kxx dx dy. That's the forward. And the inverse, let's say we define as 1 over twice pi whole squared integral minus infinity to infinity minus infinity to infinity f of kx ky e to the power plus jkxx plus jkyy dkx dky. Now again we'll try to get back to f of xy. So I have 1 over twice pi whole squared, this double integral then I replace f of kx ky from here. Okay, let me do that. I have integral minus infinity to infinity f of x comma y or x1 comma y1 e to the power of minus j k x x1 j k y y1 dkx dky. Okay, into whatever is remaining. Okay, what is that? That is d. I'm sorry here. dx1 dy1. Okay, and we have the rest, which is, let me write, dkx dky e to the power of jkx x jky y. Okay, so now we'll do whatever we did last time. Integral minus infinity to infinity minus infinity to infinity. So this is f of x, xy. Then we take 1 over twice pi whole squared inside integral minus infinity to infinity. I am shortening my steps. Okay, e to the power minus jkx x minus x1 or x1 minus x, doesn't matter, x1 minus x ky y1 minus y dkx dky. Okay, then f of x1 y1 dx1 dy1. So again what happens here, we have f of xy here, f of x1 y1 here, and an integral over an infinite domain. So what is inside here must be a delta function, double delta function. Okay, so what is inside here, 1 over 2 pi square, 2 pi whole squared, integral minus infinity to infinity e to the power of minus j k x x1 minus x minus j k y y1 minus y dkx dky must be equal to delta x1 minus x into delta y1 minus y. Okay, so therefore this part, just this part here is 4 pi square taken up into this delta function. Okay, so that part. The reason I am saying is that if you use this definition somewhere, if this definition is used somewhere, then the corresponding forward and inverse Fourier transform pair must be this. Okay, that's why I am stressing this. Now let us see here. So we are going to derive, as I said, the main central integral of Maidanik. So the geometry is this: I have a plate placed in the xy plane. XY plane. Let's say my origin is here and this dimension is A and this dimension is B. It is placed in a baffle. Okay, we know, so that communication with backside is prevented. Then there are individual modes on the panel. Okay, so this direction is mode number is M, the y direction the mode number is N. So the kpx modal wave number in the x direction for the p plate or panel is m pi by a. Similarly, the modal wave number in the y direction is n pi by b. Okay, m is the number of half cycles of the mode in the x direction and n is the number of half cycles on the plate in the y direction. Okay, and the plate for now is simply supported. So that the mode shapes are sine m pi x by a and sine n pi y by b. Okay. So now somewhere in the paper we have a power definition, sound radiated from the panel. So if you consider this to be the panel, okay, so the sound radiated is pressure seen by the panel multiplied by the velocity of the panel, okay, and the panel vibrates or has non-zero displacement only on the plate, not on the baffle. So baffle is rigid. So outside of A and B, outside of 0 to A and 0 to B, there is no displacement. Okay. So a pressure times velocity over the panel will give you the power. Okay. So we will use this definition. The power is given by 1/2 the real part of integral 0 to A integral 0 to B, okay, of P of x comma y comma 0 V conjugate x comma y dx dy. Okay, this is our starting point. Now the V velocity of the panel x comma y spatially is 1/4 pi square integral minus infinity to infinity integral minus infinity to infinity V of kx ky e to the power plus I kx x plus I ky y dkx dky. This is the inverse, double Fourier transform inverse. Then the pressure x comma y comma z is equal to 1/4 pi square integral minus infinity to infinity rho a c Ka, the density of the acoustic medium, speed of sound in the medium, wave number in the acoustic medium. Okay, kx ky divided by square root of Ka square minus Kb square e to the power I kx x plus I ky y minus I kz z dkx dky. If you remember that in 1D panel also we had a similar expression, okay, pressure x and y directions was given by rho ck by this thing acoustic wave number square minus kx square into V kx. Okay, we had this expression pressure in kx at kx wave number, if you recall in the 1D case. So this is just an extension to 2D. Okay, so this kb square, or let me put it as kp square, kp square, okay, I'll put it as kp square, is kpx square plus kpy square. Okay, okay, next hence the acoustic power, okay, I will need space here, let's see, thus the acoustic power is given by, if I put these two back in there in the equation above, so that P of omega is equal to 4 pi square plus pi square and 2, that gives me 32. So I get rho A C K A by 32 to the power pi fourth. Then the real part, okay, of an integral which is 0 to A, which is 0 to B, integral, I'll shorten my notation both minus infinity to infinity, b of kx comma ky by square root of k a square minus k p squared e to the power I kx x plus I ky y dkx dky into integral minus infinity to infinity double integral v conjugate kr ks e to the power minus I krx minus I ks y. These are dummy integral variables, and in the end dx dy close. Okay, so one thing I will say here, that the nature of v of kx ky is such that it has been derived from a vxy which is not equal to 0 only on the panel. Outside it is 0. Such is the nature of v kx ky. Okay, and therefore this spatial integral over 0 to a, 0 to b, this spatial integral, okay, can be replaced with an infinite integral, okay, because this vx is 0 outside anyway, okay, this and this are tied in such a manner, okay, that vkx ky arrives from a vxy which is 0 outside the panel. So this integral here can be replaced by infinite plus minus infinity, which is what I will do. Okay, so if we do that, okay, so if we do that, suppose I have replaced them with minus infinity to infinity. Okay, now let us see where x and y exist in the integrals. So I have x here, I have y here, I have x here, I have y here, and this is the dx dy integral. That's the only place I have x, y and dx dy. Okay, and this integral I have replaced by infinite limits. We now look at just the xy integral. So that is integral minus infinity to infinity minus infinity to infinity e to the power I x kx minus kr e to the power I y ky minus ks dx dy, and this is equal to 4 pi square delta kx minus kr delta ky minus ks. Okay, so the delta function which will force kx and kr and ky to be equal to ks. Okay, now if this result is brought into this integral above, then if kx is forced to kr and ky is forced to ks, then the remaining double integrals on kr, ks and kx, ky will collapse to one integral. So we will see that now. So we get P of omega is equal to rho a c k a by 8 pi square the real part of integral minus infinity to infinity magnitude of v kx ky squared by square root of k a squared minus k p squared dkx dky. Okay, now here this is one stage we have arrived at. Okay, now the mode shape assumed is on a simply supported panel. And therefore my v of x comma y is v0 sine m pi x by a sine n pi y by b. Okay, and this is assumed as real. Okay, this is assumed as real. Then the transform is given by integral, I will shorten my notation a little, minus infinity to infinity v0 sine m pi x by a sine n pi y by b, okay, e to the power of minus jkxx minus jkyy dx dy. So what I have done is I have shortened the presentation a little bit. Okay, so there should be a Heaviside function actually, okay, which says that my panel vibrates only between 0 to A and 0 to B. Okay, then this infinite integral and the heavy side will give us what we want. Okay. Now the complex part is only here. This is the complex part. Okay. So this becomes rho A C K A by 8 pi square, the real part of, we keep the surface integrals v of x comma y, v of x1 y1 dx dy dx1 dy1, then this double integral to infinity minus infinity to infinity e to the power of minus I kx x minus I ky y e to the power I kx x1 I ky y1 dkx dky divided by square root of k a square minus kx square minus ky squared. Okay. Now this whole part is real. This whole section, this whole portion, these are all real. Okay. So the real here can be shifted inwards. Real here can be shifted inwards. So we get rho A C K A by 8 pi square integral over surface area, integral over surface area, v of x comma y, v of x1 y1 dx dy dx1 dy1. Now the real comes in here. Integral minus infinity to infinity minus infinity to infinity e to the power minus I kx x minus I ky y plus I kx x1 plus I ky y1 divided by square root of ka square minus kp square dkx dky, where kp square is kx square plus ky square. Time is now up, so we'll stop this lecture here. Thank you.